Here we are in Aldehydes and Ketones Part 3, and we're drawing another aldol condensation where the base comes in and grabs an alpha hydrogen off of one of the aldehydes to give us the enolate. The enolate can react with the other equivalent of aldehyde to add to the carbonyl. And then that can go grab a hydrogen off of water to give us our final answer of the beta hydroxy carbonyl. And when you don't have an aromatic ring in the system, it ends up at the beta hydroxy, and then you have to take it in part 2 and add acid to it to get it to eliminate to the alpha beta unsaturated carbonyl, which is what we will draw below. So in the second step, we have the acidic water. Our beta hydroxy will go grab the hydrogen off of the water, forming the protonated alcohol, and then it'll leave, forming the cation. And then another equivalent of water will come in and grab the hydrogen off of the alpha carbon to give us our alkene. So when you don't have an aromatic ring, you have to go through 2 steps to get the alpha beta unsaturated carbonyl through the aldol. It'll stop at the beta hydroxy in the first step, and then you add acid and get it to eliminate. Now we have, since we've made some alpha beta unsaturated carbonyls, we can draw resonance structures for them to see how they're going to react. And the first resonance structure would be breaking the carbon-oxygen double bond to give us a negative on the oxygen and a positive on the carbon, and then we can send the electrons on the double bond towards the carbonyl to give us a positive on the beta carbon. So when we have an alpha beta unsaturated carbonyl, a nucleophile will either add to the carbonyl carbon or the beta carbon, because those are the 2 carbons that have a positive charge in resonance structures. So in the first mechanism below, where the nucleophile adds to the alpha carbon, not the alpha carbon, excuse me, the carbonyl, the nucleophile adds in to give us the O minus, and the nucleophile added in, then it can go out and grab a hydrogen off of acid in the second step to form our alcohol. In the second one, where it adds 1,4, the nucleophile can add to the beta carbon, send the electrons towards the carbonyl, which gives us this, and then we can draw a resonance structure for it, sending the electrons back down to the alpha carbon, giving us back the carbonyl, and then that can grab a hydrogen from our acid solution in the workup to give us our 1,4 addition. And the reason why the 1,4 it ends up at the carbonyl instead of the carbon-carbon double bond is carbon-oxygen double bond is favored. So on this page we can predict what will happen to all of these. The The only two things that we'll add 1 to are a Grignard and an alkyl lithium. And on this problem, we don't have any alkyl lithium, so the only one that's going to add 1 to is the first one. Everything else will add 1 for. So the first one will get that. The carbon will be the nucleophile there. And the third one, the nitrogen lone pair, we'll add, and we'll end up with this as our answer where we added the amine in 1,4. And the next one we have a cuprate, so the methyl will add in 1,4. And here we get a form the enolate, and the enolate will add in 1,4. So we're going to end up with a carbonyl, 3 CH2s, a carbonyl, and then a phenyl ring. And then in the last one here, it's a little different than the others in that first we will form the enolate, it'll add in, and what we end up with is after everything is done, we end up forming one. We'll have the Michael reaction where it adds 1,4, and that's forming. The Michael reaction forms this bond right here that we've drawn in red, and then once we form that bond, we can form the other enolate on the alpha carbon, and we get the double bond forming from the aldol. So what we have here is a Robinson ring annulation where we form first the Michael reaction to form the 1,4 addition, and then the aldol condensation. And then here at the bottom of the page, in the first reaction where we can cleave a carbon-carbon double bond, that would be an ozonolysis followed by either zinc and water for the workup or dimethyl sulfide. And then from there we can do the aldol where just with hydroxide we pull off the alpha hydrogen from the aldehyde and have it attack the other aldehyde that does not have an alpha hydrogen. So in this first problem, we see we're forming a carbon-carbon double bond in the first example where we have it adding on to the alpha carbon of a carbonyl. So all this is going to be is an aldol. Anytime you see the formation of something that looks like this, where we form this bond on the alpha carbon to the carbonyl, it's going to be some sort of aldol condensation is the easiest way to do that. So for this, we'd add hydroxide, and then we would add benzaldehyde, and that would form the carbon-carbon double bond where the hydroxide would remove one of the hydrogens, alpha, to the carbonyl, and then that would react with the benzaldehyde. When we want to reduce just the alkene, we would do hydrogen and platinum, hydrogen, palladium, hydrogen, and nickel. That reduces the carbon-carbon double bond. And then if we want to reduce the carbonyl, the ketone, we can use LAH, lithium aluminum hydride, and it'll just reduce the carbonyl, leaving the alkene alone. And then at the bottom of the page, we have hydroxide, which its conjugate acid, water, has a pK of 16, and the ketone has a pK of 21. And then, so the equilibrium in this reaction is going to lie towards starting material pretty strongly. In the bottom example, we have the pK of 21 for acetone and the pK for the diisopropylamine in the mid to upper 30s. So the equilibrium in the second reaction is even stronger to the right. There will be really no equilibrium. It'll go all the way to product with no starting material around because of the huge difference in the pKa's. So with the enolate, we can draw one resonance structure where we send the electrons down to the alpha carbon, and so from an enolate we can see it can react as a nucleophile from either the oxygen with a negative charge or the alpha carbon, which can have a negative charge. If we add TMSCl, trimethyl chloride, it primarily reacts on the oxygen to give us the TMS enol ether. The silyl enol ether can be cleaved to give us back the enolate by adding either tetrabutyl ammonium fluoride, fluoride ion, or methyllithium. And the reason for this, the fluoride ion or the methyl anion, is the bond to the silicon is much stronger than the oxygen silicon bond. So what happens is the fluoride or the methyl attacks the silicon and we kick out the enolate. And we reform our enolate so we can do something with the enolate to add onto the carbon. So an example of this, if we add methyl bromide, we can see the enolate reacting with the methyl bromide to form the 2-butanone. Now on the last one on this page we have the sodium hydroxide, which forms to the more substituted enolate, which is the thermodynamic. And we know we have an equilibrium that actually favors the starting material with only a little bit of it being the product. In the second example, LDA, the equilibrium lies exclusively towards the product. The LDA is sterically hindered, so it forms the kinetic enolate. So here we have a problem where we see we want to either form, doing an aldol, we're going to start with 1-methyl or 2-methyl cyclopentanone to form either of the products. And to each of them, we will add the same aldehyde because we're only adding 2 carbons on. So to each of them, it'll be the addition of ethanol. And the only difference is which enolate do we need to form. In the first one, where we need the aldol adding on to the less substituted side, where we take the hydrogen that I've drawn in black, we have to use LDA to make sure we pull off the correct hydrogen. Once we form the enolate, we can add the aldehyde, and that will give us our beta hydroxy carbonyl on the less substituted side. To form the hydrogen, or to form the aldol for product number 2, we need to pull off the hydrogen on the more substituted side. So the only way to do that is to add hydroxide, so we have the thermodynamic enolate, and then once we've added it, we can add the ethanol, and we end up with the desired product with the aldol happening on the more substituted side to give us that product.